Okay, good evening and welcome back to class. Tonight's lesson is going to be over 10.2. It's going to be an extension of our study of circles. More specifically, we're looking at chords within a circle. So let's take a look at chords in a circle. Let me create that. Here's a circle. Here's a couple of chords. Could be more than one, could be more than two, but we'll just look at two here tonight. The idea is we're looking at chords and their length and their relationship to the center. So real quick, we can make a few real quick observations, and that is the longer the chord, the what to the center, and the shorter the chord, the what to the center. And the answer to that is clearly the shorter the chord, the further away from the center, and the longer the chord, the closer to the center. And we can see even as that chord approaches the longest chord possible, which is diameter, well, we pass through the center itself. The distance is 0. A couple of things to always be aware of when we talk about the distance from a center to a segment or to a chord, we're always in reference to that perpendicular distance. So it's always perpendicular when we talk about that distance. Okay? Just like if you were to measure the distance that you are away from your nearest wall, it would be the perpendicular distance from you to the wall, not the distance from you to the corner of the wall, for example. Chicago Symphony Orchestra tickets. I'm sure my wife would like that. All right, let's move on. Look at we're going to go on to tab number 2 here, and we're going to look at our first theorem. Our first theorem. I'm trying to be consistent with blue and red. If chords are equidistant, this is my given. If chords are equidistant from the center of the circle, then what can I conclude about the distance or the length of the chords? What do you think? Well, here I've got my distances, again, perpendicular distances. That's always what we're talking about. EF is 1.65, and this distance here, FG, is 2.66. Notice they are not the same. We would say that these two chords are not equidistant from the center. Let's make them equidistant. So let's adjust this one, okay, until I get 2.66. 2.66. All right. So FG, that distance is 2.66. EF, 2.66. Well, what do you think is the case with those chords? You guessed it. They are congruent. Okay? They are congruent. Let's check that. Chord lengths. There are chord lengths. 5.42 is CD. 5.41 is trying to make a liar out of me. Well, that's a rounding error. The reason why we see discrepancy is a rounding error. Let's try this again. So we'll set those aside and we'll see if this works for another chord. Let's make the chord cross one another. They might cross. Let's get these distances the same. So I'm going to play with this one until I get 0.72, 0.72. Those are equidistant. These distances are the same. They're perpendicular distances to their respective chord. And what do we notice about their chord lengths? Their chord lengths, 7.46. Indeed, the chords are congruent. I'm feeling pretty good then about giving our conclusion. Chords are congruent. Now, what you'll always be thinking, deduce, induce. Did I deduce or induce? Go ahead and answer. That's right, I induced it. Why did I induce it? Well, I was looking at patterns. I looked at 2 examples and it worked. It seemed reasonable, so I made that conclusion, and I'm right. That is different than deduction. If we were to deduce this, we would want to be proving that it's the case for all all different chord scenarios. I'm not going to go through this proof, but I will kind of lead you to it. Okay, so let's take a look. What are some things to be thinking about? Well, never mind those measurements at this point, because we're not going to induce, we're going to deduce. That means no numbers. What we're going to use are rules and theorems and so on and so forth. However, I do have to pay attention to the blue. The blue is what I am given. So I'm given equidistance. So that means these two distances are congruent. I am given that they are the distance from F to the from the center to the chord, so that means we understand that to mean perpendicular. As soon as I see perpendicular in chords, last night's theorems should be ringing true in my ears, saying, "Oh, we've got some bisection going on." Okay. Now at this point, I made 2 hashes on this chord and 1 hash on that one, because we really haven't proven that they're the same yet. That's left for. Actually, I need to maybe put 3 there. Okay. I need one more step here to kind of use an auxiliary here that's going to make this all clear. Do you know what that auxiliary is? Think about what is that auxiliary. One important tool is the radius in this chapter. Using this radius in a clever way is going to be especially helpful. So here's my radius. If I look at that radius right there, I can see a triangle comes from that. And if I make another auxiliary here, draw it over there, I have 2 triangles. And you should be able to prove that those 2 triangles are congruent. And when you prove that they are congruent, you will be able to identify that these 2 legs of those right triangles have got to be congruent by CPCTC. I'm going to leave that for you to think about. What important fact about those radii allow me to prove that those 2 triangles are congruent, and therefore prove the chords are congruent? That's for you to sleep on. Hopefully it didn't put you to sleep. Okay, let's look at the next theorem. So that's the first theorem. And now let's look at the second. Okay, in blue, if chords of a circle are congruent, so now I've got chords that are congruent, then what can I conclude? Notice here as I play with these, in blue now is my chords. In blue is my chords, and now I'm talking about the distances here. So let's go ahead and make these distances equal. Let's see, let's make that 7.03. There we go. What do you suppose is true? You guessed it. My distances, my EF distance and my FG distances are 1.44 each. We have induced that perhaps the conclusion is that the 2 chords are equidistant from the center. Let's go ahead and type that in. Okay, chords are equidistant from the center. Now, again, we would need to deduce this. Just because we've proven the last theorem doesn't make this one proven also, even though this is biconditional from the last theorem. The last theorem went from equidistance to congruent chords. This one goes from congruent chords back to equidistance. All right. You're going to find some handy auxiliaries to be helpful in deducing this theorem. Let's go ahead and apply these 2 theorems. So applying these 2 theorems, here's my first example. Just like you are getting familiar with the problem sets. Okay, some problems use geometry to write algebra, and then you solve algebra to say something about the geometry. Okay, and some require deduction or proof. I'm going to do an example of both. This one, as you can see from the givens, probably is going to include some algebra. So I'm given circle O, and I'm given that AB is congruent to CD. I'm also given the fact that OP is 12x minus 5. OP is 12x minus 5, and OQ is 4x plus 19. Well, what theorem did we just learn? I want to find OP. I want to find that value. What is this value? What do we know must be the case? If both of these chords are congruent, we must be able to conclude then that these must be equidistant, and if these are congruent or equidistant, we can write an equation. 12x minus 5 must equal 4x plus 19. And now we're going to solve. Subtract the 4x to get 8x on both sides. Add the 5 across. Divide by 8. X must equal 3. That's not my answer. Always go back and be sure you are answering the problem. OP. So I need to plug OP back in for OP equals 12x minus 5. That is 12 times 3 minus 5. That is 36 minus 5. To get OP must be 31. 31 units. Nice example, pretty straightforward. Nice example, applying a theorem, writing an equation, and solving it. And that's a common model in a lot of the problems that we do. And let's do a proof. One proof for tonight. Example number 2. Okay, I'm given triangle ABC is isosceles. So I'm given the fact that ABC is isosceles with base AC. So if this here is my base, that means my two legs that are congruent are those. So those two are congruent. I'm also given circle P. That's basically just saying that P is the center. And I'm given that PQ is perpendicular. PQ is perpendicular to AB. And PR is perpendicular to BC. Okay. Well, what should we be thinking? If I'm thinking that this is perpendicular, then what I have found is the distance. This then is the distance. PR represents the distance from P to BC, and PQ represents the distance that P is from AB. That's what I should be thinking with that comment. Alright, so let's go to this. I think some of you have already well on your way to thinking through it. Start with our givens. We've got triangle ABC is isosceles with base AC. We've got PQ perpendicular to AB and PR perpendicular to CB. Those are my givens. Now we're going to start to deduce. What do I know to be the case? Well, let's use the theorem from today. If my two chords are congruent, if it's isosceles, they've got to be congruent. So, and if my chords are congruent, then they are equidistant and those are congruent. And we've proven what it is we wish to prove. So, we know that AB is congruent to BC. Definition of isosceles. Thus, QP is congruent to PR. Why? Well, if chords of the same circle are congruent, then equidistant. From the center. And finally, if QP is congruent to PR, then we've got triangle PQR is isosceles. Definition of isosceles. Triangle. And we have proven what we wish to prove. Never forget when you work on proofs that it's actually dynamic. Okay, this triangle really is moving and can be in any of these configurations. Any of these configurations, because they still satisfy the givens, and that is these two are congruent and these are perpendicular, as well as these are perpendicular. Doesn't matter how I position this, those conditions hold. Therefore, this will always be an isosceles triangle. And that is the conclusion of tonight's lesson. Two theorems having to do with chord length and distance from the center. You've seen two examples, one in algebra, one a proof example. All right? And so with that, I'm going to sign off. Good night. Have a good evening. See you tomorrow morning. Goodbye.